Good afternoon, everybody. I'm Metin Gürkan. I'm the Director of Center for Artificial Intelligence Research. Welcome everyone to our center's Artificial Intelligence in Action seminar. We are honored to have Dr. Neslihan Yalçın Bayramoglu with us today. Dr. Bayramoglu is an adjunct professor and senior researcher at the University of Oulu in Finland, specializing in applied machine learning in medicine. Her primary research focus has been on the application of machine learning to osteoarthritis since 2018. Her work in this area aims to enhance the understanding, diagnosis, and management of this prevalent condition through advanced AI techniques. Before her current role, Dr. Bayramoglu was part of the Machine Vision Group, CMVS, at the University of Oulu. There she worked on computer vision and machine learning applications, specifically in facial expression recognition and biomedical image analysis. Dr. Bayramoglu earned her PhD from Middle East Technical University in Ankara, Turkey in 2011, with her thesis focusing on the semantic recognition of three-dimensional data, showcasing her long-standing expertise in the field. In today's seminar, Dr. Bayramoglu will provide us with a foundational understanding of the core mechanisms driving machine learning applications in medicine. She will then go into the specific applications of these technologies in the context of osteoarthritis, sharing the latest advancements and insights in this exciting field. Please join me in welcoming Dr. Neslihan Bayramoglu. Thank you for being with us, and we are excited to have you in our center's seminar series, Neslihan.
Thank you very much for the introduction. Hello, everyone. First, I would like to thank Dr. Gürcan for inviting me to give this talk, and also Brittany for the organization. It's a pleasure to be part of this series. Today, as mentioned, I will talk about the basics of machine learning, its recent applications in medicine, and finally, its use in osteoarthritis research. Before we begin, I would like to talk about briefly Finland and Oulu, where I live. Oulu is the oldest city in northern Finland. It's located on the northwestern coast at around 65 degrees latitude. Oulu has a population of about 200,000, so it's a relatively small city. The average age is younger than the national average. It's a university city with around 25,000 students, and therefore growing international community, but still 95% of the population is Finnish. For much of the year, we have snow and sub-zero temperatures. The sea freezes over. Here you see a ship breaking ice, which is the main transportation between Hailuoto Island and Oulu. When the ice is 40 centimeters thick, they open a 9-kilometer ice road for driving on the frozen sea. And people in Oulu live cycling in all seasons. Oulu is even called the winter cycling capital of the world, and sometimes the cycling paths are cleared from snow before the roads. In winter, we have very short days, but one nice thing is the northern lights. And before coming to Finland 13 years ago, I lived in Turkey, where I was born. Therefore, I wanted to have a short video clip. Yeah, so it's a place of natural beauty, full of history and diverse culture. It has great food and plenty of sunshine. I think it's now time to talk more about machine learning. So I would like to start by asking a question. Do you know how often diagnostic errors happen in medical settings? In the US, about 5% of patients receive wrong diagnosis, and each year 800,000 Americans die or permanently disabled by these errors. I want to mention an interesting patient, Andrew, who is now 6 years old. For 3 years, he had more and more pain and his growth stopped. He had trouble in walking and he experienced severe headaches. Over those 3 years, he visited 17 doctors. And his mother then entered all his symptoms and medical reports into ChatGPT. Then the ChatGPT made the correct diagnosis, which was missed by all these 17 doctors over these 3 years. He had surgery and he's now healthy. Another interesting case is Barbara. She had a routine mammogram checkup. Despite having a family history of breast cancer with her sister and mother, Barbara had no symptoms, and her mammograms were examined by 2 radiologists, and she was found to be fortunately cancer-free. Her next checkup appointment is scheduled for 3 years later. Then a machine learning tool analyzed mammograms in that hospital and flagged Barbara. She actually had a 6 millimeter of tumor, and after surgery and 5 days of radiotherapy, she is now completely healthy. So without these AI tools' help, Barbara's cancer might not have been detected until her next mammogram examination 3 years later. So these examples show how these machine learning tools can reduce errors and improve people's health, save cost and time. But now I would like to talk about the application areas, how machine learning is transforming medicine. Here are some areas where machine learning is started to use, but it is just the beginning and the list keeps growing. So I am sure that you have heard many successful applications in these seminar series. So I will quickly mention a few. So the most common use is automatically identifying diseases from medical data, especially imaging data. For example, a study from 2017 utilized deep learning to detect skin cancer. This AI model achieved the same accuracy as dermatologists in diagnosing cancer. Sorry. Another study used machine learning to detect pneumonia from chest X-rays. This time, it's outperforming radiologists. So these were early studies, and it was very exciting. They showed significant improvements, and it raised hopes for machine learning. So let's see an example about the optimism of AI at the time. So in this 2016 video, Jeffrey Hinton talks about machine learning and radiology. Hinton, he's known as a godfather of AI and also the godfather of deep learning. So let's listen what he said.
Let me start by just saying a few things that seem obvious. I think if you work as a radiologist, you're like the coyote that's already over the edge of the cliff, but hasn't yet looked down, so doesn't realize there's no ground underneath him. People should stop training radiologists now. It's just completely obvious that within 5 years, deep learning is going to do better than radiologists because it's going to be able to get a lot more experience. It might be 10 years, but we've got plenty of radiologists already.
Yeah, so basically he suggested to stop training radiologists. It has been 8 years since he said this. So what happened after that? Well, it's pretty clear that didn't happen. In fact, there are now more practicing radiologists and we are facing a shortage. Hinton's predictions shows that how AI was overpromised back then. So while machine learning can help clinicians to make better decisions, I believe that they cannot replace doctors in the future. For instance, relying on large language models for medical advice can be risky and dangerous. But on the other hand, some machine learning applications like we saw in previous examples outperforms medical experts. For example, ChatGPT passed US medical licensing exam, and it was reported to be more empathetic than real doctors. So therefore, integrating machine learning into clinical decision system requires careful planning and control, but it is not easy. So there are many challenges in practice. If you return back to our previous list, then maybe more important than diagnosis, machine learning has been used to predict disease progression. In this study, machine learning is used to simulate detailed patient trajectories for personalized Alzheimer's disease forecasting. For example, patients with the same disease can have different symptoms, can have different progress rates, and different treatment responses. So predicting these differences is very important for precision medicine. Another exciting area is drug discovery, particularly antibiotic research. So antibiotic resistance bacteria is a serious global problem, and if no action has been taken, it could cause like 10 million deaths per year by 2050. Researchers from MIT trained a deep neural network to predict molecules with antibacterial activity. They found a new antibiotic which is different from the traditional antibiotics and effective against many pathogens. Next, we have robot-assisted surgeries. It's an active research area with partially automated tools already available on the market. And let's move to the personalized medicine. We are seeing a range of applications, including mobile apps, wearables, and voice assistants. They create like person-specific interfaces for these machine learning models. And then smart health records, they aim to enhance the efficiency and accessibility of the healthcare system. For example, in this study, machine learning model predicted 90-day mortality in ICU patients. So it could be used as a guide for transferring patients from the ICU to lower priority wards. So it will save sources and costs. Machine learning is transforming clinical trials and research, for example, by helping selecting the patients. It is used to predicting outbreaks with up-to-date data. Machine learning is also enhancing telepresence, 3D prosthetic printing, medical education. And moving forward, AI tools are already started transforming clinical practice. So my favorite one is automated clinical note-taking. So this uses voice recognition, natural language processing, and machine learning to create notes from patient interactions. So this saves time by converting the audio to text and then formatting it into clinical notes. So additionally, virtual nursing assistants and medical report generation from medical images, they can be easily integrated into clinical practice. You may notice that I use AI and machine learning like interchangeably, but this is not entirely correct. So machine learning is a part of AI, but AI doesn't necessarily have to be developed by machine learning. On the other hand, deep learning is a subset of machine learning that uses neural networks. Therefore, AI is bigger than machine learning, and machine learning is bigger than deep learning. So for example, consider these pathfinding problems like the Sokoban game. Here, the goal is to move boxes to marked locations with only pushing. So AI methods that called search algorithms can solve these problems without using machine learning. So many games and web-based maps uses these kind of algorithms to find the shortest path. In this diagram, we show the relationship of machine learning with other fields. Actually, there are other fields like computer vision missing in this picture. But you see that it overlaps with medical research, standard statistics, and clinical practice. So when I switch from the Faculty of Technology to the medical faculty, one thing that I notice is the dominance of statistical methods in medical research, and also the terminology differences. So I would like to mention some of those ones. First, the differences between statistics and machine learning. So statistics summarizes data and quantify the domain properties from samples that we currently have. It also helps like to identify the differences between groups. But on the other hand, machine learning focuses on making accurate predictions for the unseen, like the future new data. Statisticians are less concerned, I think, with these like future predictions. The other difference is machine learning doesn't require prior assumptions on the data distribution, but in statistics, there is like tight assumptions about the distributions. And machine learning performs well with big data, handling many features and samples efficiently, but statistical inferences become less reliable if you increase the features or use very large data samples. And lastly, machine learning people, what I noticed, machine learning people and statisticians speak quite different languages. They use different terminology for the exact same thing. So here's a few samples. In statistics, for example, data point means sample in machine learning, or response variable means label, output, or target in machine learning. And variable, covariate, predictor, independent variable in statistics corresponds to feature or input in machine learning. Similarly, fitting corresponds to learning. Test set performance corresponds to generalization. Another point is the term prediction. So it's used quite differently. I even had a long discussion with my co-authors about using it in one of our paper in the title. In statistics, prediction refers to forecasting, but in machine learning, prediction describes applying models to estimate or assign labels to new unseen data based on the learned patterns. So what exactly is machine learning? So if I need to give a more formal definition, it is learning the relationship between inputs and outputs. So this helps us to predict the future events. The relationship is called hypothesis. It could be also called function or a model. So this model, you usually hear the word model. So this is the hypothesis. It is defined by a set of parameters denoted by theta. And our goal in machine learning is to optimize these parameters to obtain the best results. So I also have an intuitive explanation. Imagine teaching a child what horse looks like. Teaching a computer is similar, but of course not always. One method is to show example images with labels. For example, this is a horse. The image is a sample of the horse class, and the word is its label. So let's continue showing samples to train the child. This is a horse. This is not a horse. Of course, we also need to show negative samples. This is a horse. This is not a horse. This is not a horse. This is a horse, and this continues. So how do we know if a child learned to recognize horses? It's simple, we test him. So if he can correctly identify new horse images, it shows that he can distinguish horses from other animals. So computers can do this too by looking at examples. In machine learning, this is called supervising, and I will be mainly talking about supervised machine learning in this talk. So we see many successful applications. So should we always use machine learning? The short answer is no. So first we need to consider our data. If we don't have enough data, models might not work well. And the data must represent the real world accurately. So if our training data is biased, the model may perform very poorly. If our labels are noisy, then the model will struggle to learn because you don't teach the correct labels. And also if data collection is very expensive and time consuming, then machine learning might not be the best choice. And finally, if you need to explain every decision, then we should consider rule-based programming, because most of the machine learning models are very hard to interpret and they act like black boxes. So as I promised that I will be talking about the basics of machine learning, this could be a little bit boring for the people coming from machine learning background, but as a promise of this presentation, let's begin with the practical approach to a machine learning problem. Here is a simplified figure of a supervised learning with very basic components here. So first define the problem, collect and prepare data, extract features, train the model, optimize hyperparameters, it's not here, and test on unseen data. So let's discuss these components, but I will skip some of them due to time. First, define the problem clearly. Identify what we aim to predict and what the input data is. So let's consider the example of teaching a child to recognize horses. In this case, the problem can be defined as distinguishing horse images from images of other animals. And next comes data collection and preparation. It's very important. We require images of horses and other animals in this problem, each labeled as either horse or not a horse. I would like to talk more about this data annotation because it's really important step for supervised learning. So it is the most time-consuming part. There are different ways to annotate data. It depends on what it is for. So in medical application, we often need specialists for certain tasks. In some cases, for example, we just need a single word. For example, if in detecting pneumonia in chest X-rays, specialists mark if there is a pneumonia or not, just a one word. But sometimes we need to segment parts of the images. In this case, we need to mark the boundaries of the region of interest. And like you see in this demo, sometimes there are multiple objects that needs to be labeled. Therefore, it takes quite a long time to annotate the whole data set. Another type is like point annotation. So we need to detect, in order to detect landmarks, we need to annotate these discrete locations. It's quite easier than the previous one. Also, bounding boxes can be used for image annotation. As you can imagine that the target object will be framed by rectangular box. The good thing with annotations, machine learning can help itself. So if you use weak labels or rough annotations, for instance, instead of drawing the entire boundaries, users can click points inside the region of interest. Then a trained machine learning model segments the 3D data. So if needed, users can manually adjust the annotation. So it saves quite a lot of time. And yeah. So in machine learning and statistics about data, you will come across the terms like ground truth, reference standard, and gold standard. These refer to the same thing, real or true labels that we are trying to predict. These are the real and true labels. So sometimes getting these labels could be very difficult. For example, if you would like to classify tumors from images, you might need biopsy for the true label. Therefore, labeling could be sometimes subjective. In this case, we might need multiple experts and even some experts to help label the training data. Then it becomes more costly to obtain this annotated data. Another important point about data is that it should be representative and diverse. It should reflect the problem that we are dealing with. In order to have that kind of data, it needs to be large and high quality, both in terms of labels and data. So we split the data in machine learning framework. We split the data into training and test set to make sure that the model is not exposed to test data during training. This is for a fair evaluation. So, for example, like the teachers give homework, but they use different questions for the exam. And additionally, we use a validation set to fine-tune the model hyperparameters. So this might seem a little bit confusing, but all you need to remember is that the model shouldn't see the test data during training. So let's look at, again, our problem, teaching child about horses using pictures. Imagine we didn't include any zebra images in our training data, and the child never saw a zebra during training. Now, if we ask the child whether this new image is a horse or not, so they might get confused because zebras look similar to horses. So without knowing zebras, they could make a mistake based on their limited experience. Yeah, in short, I would like to say that when we prepare training data, it's crucial that we include a wide range of examples to cover different possibilities. I have a story about the importance of data. So I spent so much time on data because it's really important. So there are many versions of this story, but here is one. In 1960s, the American Army trained a machine learning algorithm to differentiate American tanks from Russian ones. They used thousands of images from both armies. They trained their algorithm using the usual process. There were no mistake in the implementation. So the algorithm performed exceptionally well during testing. So it's almost perfect. So one summer day, the US Army did a live test. At this time, the model failed terribly. So it performed worse than random guessing. So what would went wrong? wrong. So after they realized that the training model was focusing on the background rather than the tanks. In the training set, Russian tank photos were taken in winter and American tanks in summer. So if the model saw sunny weather, it predicted American. If it's see winter, then Russian. So basically, they unintentionally built a weather classifier. So please think about the consequences of such error in medicine. After collecting data, we typically pre-process it before training our model. One step is feature extraction. Feature extraction can be defined as like identifying and selecting the most important information from dataset. It's important that after feature extraction, we still accurately describe the original data. So no information, let's say not no, but there should be insignificant information loss. So it is really important in traditional machine learning. But in deep learning, features can be learned directly from the data, so we don't need to explicitly extract features. And during preprocessing, additional steps like feature scaling, dimension reduction, or feature scaling, feature selection may also be needed. Then after that, now we choose the model for our data and requirements. Our data includes input, X and Y output pairs, X and Y's. Training the model means that finding the function parameters theta of the model that we choose. But how do we find the model parameters? So this is where the actual training happens. It's an optimization problem, meaning that we are searching for the best parameters for our model to make accurate predictions on the new data. So to do this, we start by defining an objective function. This objective function, also known as criterion, but you also hear most of the time loss function, cost function, error function. There are some slight differences, but let's skip this for now. So they are like the objective and loss functions. The function helps us to measure how well our model fits the data that we have. For example, we might use a sum of squared differences between the actual output and the predicted value as our objective function. So what makes a good model then? So if the model's predictions closely match the true labels, then it is considered to be a good model. In order to achieve this, we would like to minimize this cost function, objective function. Sometimes we maximize it depending on the context, but different objective functions forms different machine learning algorithms. And sometimes finding the best solution could be very challenging, especially for complex functions. So for complex optimization problems, we can most of the time find the global solutions. So in order to summarize that, H theta is our model that we selected among different models. It has parameters denoted by theta. And then we define an objective function, a loss function, for example, such as the difference between models' values, predicted values, and the true values. Then we use optimization techniques to find the parameters that minimizes our cost function. Now it's time to test our model. Actually, before that, we need to tune the hyperparameters, and we used validation set for this, but I will skip this too. Testing means that we are now checking how well our model performs on new data. So the test data shouldn't be in the training data. I'm like emphasizing this. We want to see how well our model generalizes to new data. Remember that. These metrics and objective functions are different. Objective function is for training, and metrics like monitor the model performance. Some of the metrics and measures that we often use for classification are accuracy, balanced accuracy, precision recall, F1 score, ROC AUC, and Beer score. Now we have seen all steps in a typical supervised machine learning pipeline. So now I would like to look into the accuracy. So it is the most common and intuitive measure. Actually, it simply measures how often the classifier correctly predicts. It's the ratio of the number of correct predictions and the total number of predictions. At first, it seems to be a perfect way to measure the performance of a machine learning model. Let's look at an example.
Let's imagine that you're a chief radiologist at a hospital. By the way, we might have that person in our audience. The workload in your department is quite heavy, and in your hospital you face with many pneumonia cases. Therefore, you decided to employ a clinical decision support system with the hope that physicians can more accurately and efficiently diagnose the disease. You would like to have a machine learning-based classifier that will correctly diagnose the presence pneumonia in X-ray images. Our problem is thus a binary classification where the inputs are chest X-ray images and the output is one of two classes, pneumonia or non-pneumonia. Two companies have already developed such a system. And now they demonstrate their models to you. Representative of company A says that their machine learning-based model could analyze a single X-ray image in 10 seconds. And their accuracy is 96%. It sounds quite good. Let's have a look at the other company's product. Company B has a model that takes 30 minutes to analyze a single chest X-ray image, but they have an accuracy of 99% in detecting pneumonia, which the company is proud of. Both companies ask similar price. Now, the question is, what would you decide?
Yeah, so Brittany, could you please start a poll? So I would like to ask you about this.
Let's imagine.
So Brittany, could you please start the poll?
It says it started up. Do people see a place to vote?
Okay, sorry, it didn't pop up in my screen, so maybe
Oh, people
can
started
give-
voting. I see.
yeah, maybe we can give 10 seconds and then maybe you can tell the results.
Okay, so we'll give it a little bit more time. People can put in their votes.
Yeah. Could we now see the results?
Yeah, so we got, okay, just got a couple more votes coming through. So currently we have a 71% voted for company A, 29% for company B.
Okay. Yeah, you started thinking and the representative company B. So we have some comment on the chat box, but maybe we can talk about it later. So you started thinking and the representative of company B offers something else. Let's see.
You started thinking and the representative of company B offers something else.
Unfortunately, we have a very slow algorithm and it takes half an hour to analyze a single X-ray image in one computer. But who cares the processing time? We achieve 99% accuracy. We could run our algorithm on a super powerful server that is equal to the processing power of 200 processor, and the processing time could drop to 9 seconds. We can build the server for you for free as long as you use our software.
Okay, now things seems to change. What would you do now?
Yeah. Would we do the poll again after this new update?
So a new poll has just been posted for you guys to answer.
Okay, thank you.
Okay, so it looks like we have 100% voting for company B at this point.
Okay, 100% company. I'm really surprised to see this. Okay, thank you very much. Yeah, so what should we do? Actually, we shouldn't decide yet because first we should use the same test set to evaluate and compare different models. So we don't know which test set did they use, this company A and company B. So we need to collect a big and diverse data set, and we should use the same test set for different models. This is first thing. The second one, that we shouldn't trust accuracy metric at all. But why? I will explain shortly. So assume that this radiology department test has about 2% pneumonia cases. So it's a very imbalanced classification problem with only 2 positive samples. Now let's evaluate a classifier using this test set. Assume we have the predictions with 1 positive sample classified correctly and the other incorrectly as negative. So the accuracy, when you calculate the accuracy of this classifier, the accuracy is 90%. The model has a very low false positive rate, which shows a very good performance. So, but the model predicted, when you see from the illustration, the model predicted 11 positive samples and only 1 of them is true positive. So the precision is very low. So 0.09. So it shows that the classifier is not able to distinguish negative and positive classes. It's biased towards predicting the negative class. So accuracy is not useful when the target class is well balanced, but it's not a good choice with imbalanced data. Now I will make this classifier even worse. So I will make this classifier faulty one. So such that it predicts the negative class for every input. So whatever you present, your model, it predicts the negative class. So it's a fault classifier. So what will be our confusion matrix? This one. And what will be the accuracy? What do you think? The accuracy is 0.98. So it is now higher than before. So therefore, accuracy is not a good metric unless you have balanced data set. And in reality, in almost all data sets in medical domain, especially, are imbalanced. Therefore, we should be looking for other metrics. What metrics we need? There are metrics that can handle this class imbalance. One of them is balanced accuracy, and the other one is the precision recall, and you can use the area under the precision recall. So unfortunately, we don't have time to cover the details. And I have been talking like the supervised machine learning problem in this talk, but there are 3 broad categories of machine learning. So the most developed branch is supervised one. The other 3 broad categories are unsupervised learning and reinforcement learning. We can also have semi-supervised learning, self-supervised, multi-instance learning, multitask learning, active learning, online learning, transfer learning, and ensemble learning. So usually newcomers to the field often think that the machine learning is like a magic box that can solve every problem. But unfortunately, it's not a magic. So it is just the application of a mathematical formulation to a data. So sometimes the data doesn't learn the way you would hoped. For example, the data bias that we discussed in the Russian tank problem. So one important thing that we need to remember, that machine learning models cannot create a new knowledge. So we have to be very aware of the limitations of the machine learning, especially in this healthcare domain. So now, how many minutes do we have? I couldn't follow, but now I will continue with the second part of my talk, knee osteoarthritis. It is shortly called OA. It's a very common and progressive degenerative musculoskeletal disease. While I'm talking, you can see the animation that shows the stages of knee OA in this animation. The condition causes pain, stiffness, and limitations in movement, and many risk factors behind it: age, obesity, injury, gender. And unfortunately, the incidence of OA is increasing because of the aging population, especially in the Western countries, and also the obesity. So as a result, it creates a very heavy burden on patients and also on society because of the reduced quality of life and treatment cost and also time of work. Although there is extensive research efforts in this field, we still don't have enough understanding, and we don't have disease-modifying drugs for OA. And the interventions actually provide only modest benefit. Therefore, it's very important, and it's very important to early identification and treatment of this condition. So it's also important to understand, have a better understanding of the disease from the research point of view. Currently, the OA is diagnosed by clinical examination and usually with X-ray imaging. And if needed, other imaging modalities like MRI is used. But generally, it is diagnosed at a very late stage. Therefore, it's very difficult to manage the disease after this point. Usually, we can observe the characteristic features of OA in X-ray imaging. For example, bone, the joint space narrowing, these osteophytes, sclerosis, and cysts. But we know that the soft tissues are also associated with OA. So they are not visible in radiographs. We can detect them in MRIs, but still, we need X-rays for the complete detail of knee. In clinical practice, the severity from knee radiographs evaluated based on Kellgren and Lawrence grading. The grade is from 0 to 4, increasing as the severity of OA increases. The main problem with this kind of grading system is that they suffer from significant inter and intra-observer variation. And recently, the number of machine learning studies in OA research has exponentially grown. So besides deep learning progress, the growth is driven by two major public datasets, MOST and OAI. So they have thousands of participants with years of data, including imaging, clinical information, and so also the patient questions, expert assessments. We also have the expert assessments. This is very valuable, and it provides us labeled data. So this is the driving force of these machine learning developments in this field. So machine learning is often used in OA to grade a disease severity using this system that I mentioned. Our group developed a machine learning model for this knee OA severity classification from radiographs. Both these datasets, MOST and OAI datasets, were used, and this model achieved a very high quadric kappa. The machine learning also used to predict the progression of OAI. Again, from our group, Igor introduced a multi-model deep learning-based method for predicting the progression of knee osteoarthritis. Another popular area in this research domain is to estimate the time to knee replacement surgery. So in this study, a survival analysis model was developed using both imaging features, imaging data, medical imaging data, and clinical data. So they observed that integrating clinical variables with imaging features resulted more accurate estimates compared to like the models using only imaging features. So in this, for this specific problem, we can say that clinical variables and imaging data are complementary to each other. Machine learning is used to segment the knee compartments for analysis. For example, cartilage segmentation was traditionally done manually. Our group developed a deep learning-based model to automate this segmentation. With this model, one can efficiently segment and extract cartilage-related imaging biomarkers for further studying the progression, for example. Machine learning is also used to analyze different phenotypes. Here, the aim is to identify subgroups and identify which type of people respond to specific interventions. It has also used for gait analysis in OA patients. Majority of the research studies and clinical practice, osteoarthritis have predominantly focused on tibiofemoral joint. It is the part of the knee that is responsible for sagittal movement. You can see in this video, but there is another joint called patellofemoral joint, so the kneecap. It's a very special joint, and unlike a tibiofemoral joint, the patella rotates and translates, and it has considerable freedom of movement relative to the femur. So it also exposes to weight-bearing loads. Some studies indicate that the knee osteoarthritis commonly begins at this joint before spreading to other areas, and this type is both prevalent and clinically important because it is associated more with pain and functional limitations than tibiofemoral OA. So therefore, because of these things, over the past few years, I have chosen to concentrate my research on this joint. So we presented the first study to automatically detect radiographic patellofemoral osteoarthritis from imaging data. So first of all, we need different kind of views, such as lateral knee images. So initially, we applied a deep learning-based object detection to identify the region of interest. In this case, the patellofemoral ROI. Then we utilized these ROI as input to the second deep neural network. We also developed more traditional machine learning models using clinical data, age, sex, BMI, and WOMAC score. But these models' performance were very modest. But our deep learning model using imaging data had a very high discriminative ability. Later, we examined the bone texture to detect patellofemoral osteoarthritis using machine learning, and we conducted extensive experiments to show how texture features affect diagnostic accuracy. We showed that the texture features of patellar bone are different between knees with and without patellofemoral OA, and we obtained a very good classification performance with this model. And these results also indicate that the bone structure seems to change during this disease. And in our recent study, we utilized machine learning to predict the radiographic progression of patellofemoral osteoarthritis, again using deep learning and machine learning. We compared different models, and we also used attention mechanisms, and we combined this model with the clinical model, and the predictions from the clinical model, the increase when we integrate the clinical model with the imaging model, it wasn't very significant, but we had a slight increase in the performance. So this study is the first to predict the progression using imaging data. And we used attention maps, as I said. In various cases, the attention maps highlighted the joint space and the regions where osteophytes typically occur. So these regions are known to be affected in this disease. And finally, I recently began investigating the pain component, but analyzing the OA pain is very complex because it varies and it's highly individualized. So in this study, we aim to determine if pain has a structural component or any relation to bony changes. Our results suggest that imaging biomarkers could be used for identifying OA osteoarthritis pain. At least for some patients, we can say that structural changes are associated with their pain experiences, and I would like to continue this pain component of the osteoarthritis in my next work. So this is the end of my presentation, but maybe we can talk about the results of this in question Q&A in this accuracy. So I would like to conclude my presentation with this slide. You can reach me from neslihan.bayramoglu@olu.fi. Thank you very much.
Thank you. On behalf of everybody, I'm clapping. This was a fascinating presentation. Thank you so much. This was really, really great. And then you explained some really difficult concepts so well, and then you tied everything back to your current research. This is fantastic. So I will encourage people to put their questions in the chat. Earlier, Peter was questioning when you were polling the audience, and then he was making a comment saying, wouldn't the false negative rate be the most important item to know? You don't mind reviewing many normal X-rays, but you don't want to miss a pneumonia or cancer. I think that was clarified in the presentation, but if it is still confusing, please put it in the chat. While people are thinking about what to ask you, I want to ask you a question about a little bit more on a philosophical level. So when we look at, for instance, KL scores, and then and it's not specific to osteoarthritis or radiology. In many cases, we have these classification systems, and these classification systems are developed to be practical, because you cannot have a really large number of categories. It's not practical. It will be really difficult. But in many cases, there are 3 categories, 4 categories, and then these are optimized, created by human readers. and then optimize for daily clinical value. Do you think it is time for us to reconsider these categories in the age of AI? Because AI can actually generate many more categories or can consistently evaluate them regardless of how many subcategories that we have. So I just wanted to hear what your thoughts are. I'm not specifically, trying to attack KL or anything like that, and KL may be really good, but I just wanted to ask a more general question motivated by KL.
Yeah, so I completely agree that so there are many issues with this KL grading and could be with other grading as well. So one of the issue with these kind of things, so we are not trying to estimate the severity of the disease, but we are like trying to replicate the assessments. So if there is like a how to say, if there is not a direct relation between the disease and this KL grading system, so what is the use of this classification, or what is the use of making this kind of assessments? So I think it is not very difficult to just see an X-ray and recognize the status of the disease. And sometimes the clinicians even doesn't need to take X-rays in order to diagnose the disease. But on the other hand, we really need to process like a very large batch of images in order to further analyze like the big data. So in clinical practice, we really don't need the KL grade. So when you go to visit with the clinician, they really don't care much about the severity if you really don't need, for example, the knee replacement. Because you might have some mild symptoms and mild X-ray features, but they really don't write in the clinical notes KL2 or 3. I never saw something like that. So we use it for the research purposes in order to evaluate like the progression. So in order to define the progression, we have to like put some kind of grades to images or the knees and the data. So I think it is useful in that sense, but I agree that we should look from a different point of view when we are like classifying or evaluating the diseases. It should be like we should be looking at a bigger picture. So not just the imaging data, but we should be like looking at the personal level. For example, if one person age over 45 goes to a clinic, and if we take an X-ray, we might see like the collapse of the joint, but the person might not have any symptoms. On the other hand, we see no signs of osteoarthritis in X-ray, but the person comes with a very severe pain.
Yeah.
So it is in case of osteoarthritis, we really don't have a clear understanding of the disease, and we really don't know what changes like the imaging biomarkers are, what changes are related with normal aging, and what other changes are related with the disease. So I'm not sure if I answered your question, but
No,
yeah.
I think you did. Just it is. I think this is. We truly have the opportunity now to do personalized medicine with the help of these tools. So we are not limited to only a small number of categories for our patients. We can potentially increase those, and then by looking at their healing trajectories, right?
Yes.
So there are a couple of other questions. One question is
I'm so sorry,
motivated.
I couldn't see the chat.
That's
chat
all
box.
right. I'm going to read them to you, and then I will also put them in the context. One a question is related to the again motivated by the poll question. So they are asking when it comes to deciding which algorithms to use or purchase, who should make that decision? Is that the decision of the radiologist? Is that the decision of the AI scientist? Is that the decision of the hospital? And then, of course, in Finland, it may be that the government may be the main payer. Should it be the government? So, what are your thoughts on that? Who decides on which algorithms should be used or purchased for clinical purposes?
Yeah, I think the government should decide or can only decide the funding model. I think it would be so difficult to ask them to decide which model and which unit it will be used. But I think it should be like a agreement from both machine learning scientists, researchers, and also clinicians, and also the hospital admin, because there are different parts. The clinicians is going to use this one. So it should be the user interface and how it explains the explanation, how it conveys the findings of this machine learning model. So it is important. They are the users and they are going to interpret the results. So it is important. They should be included in the decision. Also, the machine learning scientists, they are going to evaluate the effectiveness and the problems with associated with the models. So they should be included. And these systems needs to be integrated with the hospital system, like the PACS system. They need to extract data from the PACS. They need to be integrated with this infrastructure. Therefore, the hospital admin also be included in the decision-making process. These three.
There are many aspects to this one. Genesio is asking, can machine learning use genomic data without images to predict disease status?
Yeah, I didn't put it in my slides, but it has been already used. It has been using for genetic studies and genomics. And actually, in osteoarthritis, there should be a few studies about it. So it has been already used. So we don't really need on imaging data, but it is very popular, and it is it's a very good data structure for convolutional neural networks, because you have a 2D grid and you can convolve it easily. So it is very well defined. But otherwise, you can use many different. Also, you can use the temporal, like the time series data for machine learning. So you can use many data as long as you define the problem and you have well-defined input and output.
Yeah. And I'm glad that you talked about Dr. Hinton's comment.
Yeah.
For some people, it may sound like an innocent comment and an AI scientist getting excited and making a comment like that. Actually, it had a serious side effect. A lot of people decided not to go into radiology, and some radiologists were seriously very concerned about those comments, and we still hear from some of our medical students. So I think just, as AI scientists and people working in the AI field, we need to be a little bit more responsible and careful about what we say, because people get scared and they are afraid, and then there are some of the comments can be really misunderstood. Maybe if you have a few more words on that, that would be really good before we close.
Yeah, so I agree with you that I also heard from maybe junior radiologists, they were like frightened and they keep a distance with the AI. So this made them frustrated about the technology. But if the approach was different, the approach should be like this. I think the next successful radiologists will be the ones that integrate AI into their clinical work. They shouldn't be frightened. They can learn the basics. They really do not need to develop machine learning model themselves. Of course, there are now programs. I heard like double degree programs like medical faculty plus computer science. So not everybody needs to be enrolled in those degrees, but it would be nice to know the basics of machine learning, and it would be nice to be able to use them in their clinical practice or research work, whatever they are doing. So they will be the successful ones. And as I said, that as I give the numbers, unlike Hinton's suggestions, the number of radiologists increased and the demand is now more than before.
Mary Hoy said, thank you. Really enjoyed this very informative presentation. And I think Mary spoke on behalf of everybody who attended this talk. It was really remarkable. We really want to thank you and then congratulate you. And then thank you for sharing your contact information. Some people may get in touch with you. And then hopefully you will come and visit us and then meet with our researchers at some point. And
I
then,
would be really happy.
yes. So on behalf of everybody, I'm clapping. And then thank you. Have a nice evening, everybody. And if you are not a member, please become a member. And then follow our activities. June 28th, we are going to have a really big workshop on AI. And today is the deadline for registration. So if you forgot to register, just you have a few more hours to register for the June 28th event. Thanks so much, Neslihan. Great seeing you, and then wonderful hearing your presentation. Have a nice afternoon and have a nice evening. Bye-bye.
Thank you very much. Bye-bye.